Okay, ladies and gentlemen, this problem has to do with an equilateral prism, and gee, we have a nice icon for an equilateral prism right there, right there. The index of refraction of this prism, 1.5, and you'll recall that's the velocity of the speed of light divided by the velocity of the wave inside a prism. We're going to go like so. So the wave, it hits one interface, it's going to go to the next interface, and then it's going to exit. There we go. And we have to just work through the angles. I'm drawing my normals now to the interfaces. I might have to make a second drawing, a bigger drawing. So this is the angle of entry. I'll call this angle 1, angle 2, and I'll make it bigger. So angle of entry, and this is theta 1. So that this is where it enters the glass. And on the other side, it's coming out. I'm just drawing the two crosses just to give us a normal. It's coming in like so, and this is theta 2, and then we're going to get theta 3. Theta, let's see, enter theta x for exit. Okay, so we want to know what theta 2 is. So part A is asking you, what does theta 2 have to be for total internal reflection? I'll underline it, total internal reflection. Well, that's kind of easy. And we're presuming the outside, we're in air, and we're presuming the index of refraction outside is 1. So 1 times n times sine theta, so 1 times sine of 90 degrees equals 1 equals n2. Oh, excuse, yeah, n2 times sine of theta 2. Well, this is n2, 1.5. So sine of 1 over n2 equals. And once we got that, we can get the inverse sign to get theta 2. So let's go to our handy dandy calculator and do 1 divided by 1.5. And I can do that in my head even, 0.667, and do the inverse sign. I can't do this in my head. There we go. 41.8 degrees is theta 2 then. Which makes this angle here 90 minus 41.8. Let's just label it theta 3. We're going to need it. You have to use geometry to work it backwards. And that's what I'm doing. I'm doing part B, using my geometry to work backwards. 90 minus 41.8 equals I'm going to store this just to make sure that I keep it around. So I've got 48.2. Looking at this, just drawing it nice and big, I've got this going on. This is 60 degrees at the apex. It's equilateral. I may give you a different prism. 45, 45, 90, 3, 4, 5. I may do something different. Now, theta 1, we're calling this theta 1, is just these three angles have to sum to 180. So theta 1, angles have to sum to 180 degrees in a triangle. Minus 60 minus 48.2. So inside the glass, theta 1, or inside the glass, equals this expression. Go back to our calculator, calculate away, change sign, take away 60 equals 108, and we add 180 to it, and I'm just using negation to perform subtraction. That's all I'm doing in the calculator. 71.8 degrees. Okay. And now finally, speed of light inside the glass. Well, we can calculate the entrance angle. Let's just do that. Some of you may think that you have to get this far. It's just application of Snell's law. So n1 sine theta 1. In this case, we'll take this to be the entry, and n1 is 1 equals index of refraction inside the glass times sine theta 1. Since n1 equals 1, we can get that. Let's go back to our calculator. The sine of this is 0.95. Multiply it by n, which is 1.5, equals. And then we take the inverse sine of this to get the angle, finally. Theta E is, ooh, something's wrong. Oh, I know what's wrong. I blew it. This is not, I don't use 71.8. This is 71.8. I need to measure from the normal all the time. So I need to take 90 minus the 71.8. And this is actually not theta 1. This is some random angle. I'll call it theta 4. This is theta 1. So theta 4 is 71.8. That makes theta 1 equal, get my calculator back up. Recall, just do the calculations over again. That is 78.1, and I gotta subtract that from 90. There we go. Sheesh, what's going on? Okay, let's get that one. Add it to 90 equals 11.8 degrees. 11.8 degrees. Now, when I take this, and the formula works with this, measuring angles from the normal. Snell's law is angles are from the normal, and once we do that, then we ought to get a reasonable result. And this illustrates the process. Nobody's perfect. Everybody makes mistakes. It's important just to be calm and find and fix your mistakes. So we get theta entry. Theta in the air outside has to be 17.9 for it to be 11.8 inside, for it to be 48.2 on the other side here, and for this angle to be at the critical angle of 41.8, and the exit That's where the borderline between total internal reflection getting out and getting in the glass. This is the critical angle. 41.8 is the critical angle. Last question. What's the speed of light in glass? Well, the index of refraction is the speed of light in vacuum over the speed of light in glass. And just solve for V. And I can work that out in my head. I'll go to the calculator anyway. 3 times 10 to the 8th meters per second is the speed of light. It's right here up in the problem statement. And we have to divide that by the index of refraction, which is 1.5. 2 times 10 to the 8th meters per second will be the answer. And we are done with this problem.